We shall now describe how much compatible principle of linear superposition is with respect to a differential equation that describes a system. Any physical system for its description needs a differential equation. Differential equations are set up for a system based upon certain logics, and then this differential equation is solved to get various features or characteristics of the system. So these are the steps. Let us consider a differential equation, say where omega 0, alpha, beta are constants. The question is principle of linear superposition compatible with this differential equation corresponding to certain system. Suppose x1 is a solution of this differential equation, and also suppose x2 is another solution of this differential equation. x1 is a solution of this differential equation, so you can write and again x2 being a solution, we can rewrite this equation with x2 let us add them to get x1 plus x2 x1 plus x2, and here we have x1 square plus x2 square and beta into x1 cubed plus x2 cubed. It is clear that x1 plus x2 does not occur with alpha or with beta, and therefore x1 plus x2 is not a solution of this differential equation. So what we get is, if x1 is a solution, if x2 is a solution, then a linear combination of these solutions is not a solution of this equation. This means the principle of linear superposition or linear combination does not hold for the system which is described by this equation. and it does not hold because of the presence of the square term and the cubic term. In other words, this is a nonlinear differential equation. So let us write because it is described by a nonlinear differential equation containing terms like x square, x cubed. Now suppose that alpha is 0 and beta is 0, which means we get rid of the nonlinear part. So let us set up the problem. Consider a system that is described by this equation where omega 0 is a constant. This is obviously a simple harmonic oscillator equation. So the system is an oscillator, simple harmonic or linear oscillator. So the question is principle of linear superposition compatible with this differential equation that describes a system, to be precise, an oscillator. We will proceed in the same manner. Let x1 be a solution, let x2 be another solution. And they are independent solutions. Since x1 is a solution, let us rewrite this equation, putting x1 for x. Even if we multiply by a constant c1, what we get is and since x2 is another solution, and if we multiply by c2, which is a constant, and let us add these two equations. We have c1x1 plus c2x2 it is clear that c1x1 plus c2x2 is a solution. So, if x1 is a solution, if x2 is a solution, then we can combine them linearly by multiplying with a constant c1 and c2, after which we get this linear combination c1x1 plus c2x2, which will also be a solution. And this is nothing but principle of linear superposition. So let us write it down. If x1, x2 are independent solutions, then their linear combination is also a solution. And this can also be written using the summation sign. And this is principle of linear superposition. So, principle of linear superposition is compatible with the differential equation that describes a system, say an oscillator. Let me reiterate that why is it linear? Because in the solution we have x1 to the power 1, x2 to the power 1, and therefore it is linear. And why is superposition? Because of the presence of this plus sign or the summation sign. Because the solutions being added makes no difference, it is still a solution. And this has been possible because the equation, the differential equation that describes the system is linear, because this is raised to the power 1, so it is linear, and there are no x square x cube terms, so its degree is 1 because the highest order is raised to the power 1, so degree is 1, so it is a linear. It is second order because the highest order is 2, and there are no x square, x cubed, etc. terms are there, and therefore principle of linear superposition holds. We now mention how principle of linear superposition is often written in physics. So representing principle of linear superposition, in fact we'll write down the law of additivity. In this method of writing, the effect of system on which stimuli is applied is denoted by the letter T, T for transformation. So x1 is a stimuli, x2 is another stimuli, which are applied on system, and the system responds. The response is now written in this notation, T of x1, T of x2. T means transformation. Let us write it in third bracket. This is the practice which is done, and now we multiply it with C1, which is a constant. Here we multiply it with C2, another constant. So we have C1 T of x1, and here we have C2 T of x2, and they are added. As a result of which, what we get is C1 T of x1 plus C2 T of x2. Now, on x1, let us apply C1. We multiply x1 by C1 to get C1 x1, multiply x2 by C2 to get C2 x2, and then add. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . and then we have C1x1 plus C2x2. This is applied on the system, the response being T of C1x1 plus C2x2. For principle of linear superposition to hold, that is, for the system to be linear, these two have to be equal. So they are same. And therefore, the condition can be written as so this is the condition for linearity of a system. This is the condition for validity of principle of linear superposition. Again, let me reiterate that T stands here for transformation, and also that this side represents the response of system due to collective application of stimuli on the system, while this side represents the response of the system due to individual application of stimuli. This was discussed in earlier video. Let us now go to application. We discuss cases of systems showing linear response. So in this column, we'll write down the stimuli, the response we'll write down here, and the nature of response we'll list in this column. The general rule is that if the stimuli is high, that is, if we hit a system, if we push a system mercilessly, then the response will be large and the system will move or system will behave in a non-linear fashion. So non-linearity is induced in the system if stimuli or the disturbance is very large. On the other hand, if system is caressed, if system is just touched or nudged, that is, stimuli is feeble, then the response will be very low and the system will act in a linear fashion. So the response is linear for a low stimuli and the response is non-linear for a high stimuli. Let us now mention cases where systems behave in a linear fashion. Suppose we apply voltage to a circuit. The circuit responds by sending a current and I is proportional to V as per Ohm's law, which is a linear relation. Suppose a system is acted upon by a stress and the stress amount is very small, that is within elastic limit. The system will respond by developing a strain and stress and strain are proportional to each other because the stress is very small. So Hooke's law, that is the law of linearity, holds for small stress within elastic limit. Consider that a small electric field is applied on a dielectric. So small as not to cause a dielectric breakdown. So there is no dielectric breakdown. The dielectric responds by developing a polarization, and the polarization is proportional to the electric field, and the proportionality constant will be the electric susceptibility. Suppose on a magnetic system we apply a small magnetic induction. The magnetic system will respond by developing a magnetization, and for linear homogeneous isotropic magnetic medium, M and B are proportional. For instance, the system turns into a paramagnet. So the essential relations here shown are linear, but the criteria or condition is that the stimuli should be low. We will now discuss linearity as well as non-linearity with reference to an oscillator or a pendulum. So now we discuss the pendulum equation. And will not consider any damping. The pendulum equation is given by this is the equilibrium position or equilibrium line, and the pendulum say is released from this point, so this angle is theta 0, and during its swing it assumes this position, and this is theta at time t, and this is say at t equal to 0, at which the experiment has started. So this is the point of release. Now what is L? L is the length, M is mass of bob of pendulum, theta 0 is the angular displacement of the point of release of the bob or the mass m. It represents obviously the maximum amplitude. It is the limit of swing. Pendulum cannot go beyond theta 0, and theta 0 also represents the energy that is pumped into the pendulum for it to swing. Here omega 0 is under root g by L, where g is acceleration due to gravity, and we have theta. Theta is angular displacement, at some intermediate time, say t. Theta and theta 0 are in radian. This is very important. And what is sine theta? Sine theta, as we know, is a series, infinite series. So the first few terms are factorial 5 is 120, factorial 3 is 6. Let us now discuss a linear pendulum. In which the value of theta 0 or theta is small, tends to 0. To be very particular, it is less than or of the order of 4 degree, that is 0.07 radian. Actually, theta should be less than, much less than 1 radian, and here it is 0.07 radian. So the criteria is satisfied, so that we can now, instead of sine theta, just take the first term and write theta only, because these are very small. This is small, this is smaller, so you can neglect all the terms and retain only this term. So this is a linear approximation that we make, because theta is raised to the power 1, and therefore this pendulum equation takes the form instead of sine theta we will write just theta, and we have a linear differential equation. There is no theta cubed or theta to the power 5, etc. Solution is and omega 0 is the frequency, and the time period is so this is the time period. So the main point is that the pendulum oscillates over a linear path. This path is nearly linear because of this linearity approximation. We now discuss a non-linear pendulum. Sine theta, which is expressed in a series, is theta minus theta cubed by 6 plus theta to the power 5 by 120, and it goes on like that. Let us approximate sine theta as theta minus theta cubed by 6. In other words, theta is small enough that justifies neglect of terms like theta to the power 5 and its higher powers. So with this approximation, the differential equation becomes so it is non-linear because of the presence of terms like theta cubed. We can solve this equation. The solution is a complicated one, and it can be shown that the frequency is given by and the time period is given by clearly frequency decreases and time period increases due to non-linearity. So the effects of non-linearity on the pendulum is to decrease frequency, increase time period. We now mention the differences between a linear system and a non-linear system. Law of linear superposition, this is obeyed, but linear superposition is not obeyed for a non-linear system. Next, law of additivity. This is obeyed in a linear system but not obeyed in a non-linear system. Law of homogeneity or scaling. This is obeyed in a linear system. This is not obeyed in a non-linear system. Differential equation that describes a linear system is linear, and there are no terms like x square, x cubed, etc. But to describe nonlinear system, we use differential equation, which is nonlinear and involves terms like x square, x cubed, etc. So these are present. Next, solution of the differential equation is simple, but for a nonlinear system, the solution is very complicated. Regarding complexity, we mentioned that a linear system is simple because it is linear, but the complexity of a nonlinear system is large, so it is complicated because it is nonlinear. We now give example of linear system. For instance, the output is x of t or x f of t or say f of t x of t. For systems which produce this type of output, we'll say it is linear, but if the output is say f of t plus x of t, then system is non-linear as discussed in previous video. So these are non-linear systems. And let us also give a physical example. A simple or linear pendulum is an example of a linear system, and anharmonic oscillator or anharmonic or nonlinear pendulum is an example of nonlinear system. Here theta 0 is less than or of the order of 4 degree, but here theta 0 is greater than 4 degree, that is allowed, and sin theta can be taken to be theta minus theta cubed by 6 as an approximation. And here frequency falls and time period increases compared to a simple pendulum. And here this approximation has been made, linearity approximation.